When we talk about limits at infinity, we're talking about what happens as x goes to infinity and minus infinity. So just to orient ourselves a little bit, let's imagine some function with finite limits as x goes to infinity and negative infinity. Here we go. Here's a nice function. We'll call it f of x. And note that we're not really concerned in this context. We're not concerned with what happens in the middle, right? This doesn't really matter. We're more concerned with what happens as we go out further and further. And assuming that this function just continues on like it is now, we can see two different limits. One is x goes to infinity, and one is x goes to negative infinity. Okay, we can even sketch these limits in. These are known as horizontal asymptotes. And note that it's okay for a function to cross the horizontal asymptote, right? We're more interested in what it does eventually as x goes to infinity. So here we would say that the limit as x goes to infinity of f of x is 3, because that's what it's approaching as x goes out to infinity. And we say that the limit as x goes to infinity of f of x here is negative 3. So it's easy enough if we have the graph of the function, but let's look at some ways to develop this analytically for when we don't have the graph or when we're trying to create the graph of the function. So here we have 4 examples of limits at infinity. The first one, part A, says the limit as x goes to infinity of sine x over x. Now this one's a little different than most of the other limits at infinity that we'll see, because it has this oscillating sine x going on in the numerator. So let's treat this as kind of a special case here. Now qualitatively, we can probably just give this a little bit of thought and convince ourselves of what happens here, right? Sine x is trapped between -1 and 1. So no matter what happens, the biggest it gets is 1 and the smallest it gets is -1. But x itself is just getting bigger and bigger and bigger. So sine x can oscillate as much as it wants between -1 and 1, but this x in the denominator, as that goes out to infinity, it's just going to pull the whole thing down to 0. And indeed, if we look at a graph of sine x over x, you can see that the function itself is getting pulled down closer and closer to 0 as we go further and further out towards infinity and negative infinity. So qualitatively, we can say that this thing equals 0, but we need to do a little bit more mathematically to show that. Well, since sine of x is a maximum of 1 and a minimum of -1, we can trap that between -1 over x. We can trap this whole function between -1 over x, so it's less than or equal to sine x over x, which is less than or equal to 1 over x. Now, both of these end functions go to 0 as x goes to infinity, right? We just essentially plug in infinity for x. I know that's not mathematically sound, but that's really what we're doing here, essentially. And infinity is just going to pull those things both down to 0. So then by the squeeze theorem, this middle function, sine x over x, also must go to 0. And I won't rehash the squeeze theorem here. There's another video on that. I will link to it in the description of this video in case you missed it. So there is a rigorous explanation of why the limit as x goes to infinity of sine x over x equals 0. It would be the same thing for the limit as x goes to negative infinity. And there we've shown it. So from now on, we can use that result, and we don't need to show that every time. We don't need to keep using the squeeze theorem. It's okay to just say, hey, that's 0 as x goes to infinity. We know it is. And if pressed, just break out the squeeze theorem, and it's pretty quick to show. On to part B, where we use this result. We have the limit as t goes to infinity of the quantity 5t squared plus t sine t all over t squared. And there's one crucial key that's very useful in calculus for evaluating these limits at infinity. So here's the key. Divide everything by the largest power in the denominator. And we'll use this in various forms again and again as we evaluate these different limits at infinity. Okay, so what does that mean in this example? It means we look at the denominator, we have t squared. So I'm going to divide that by t squared. As long as I do it to the numerator as well, we're okay. So I'm dividing the 5t squared by t squared and the t sine t by t squared. Why does this work? Well, I'm really, just as an aside, I'm really just multiplying the top by 1 over t squared and the bottom by 1 over t squared. Whoops, t squared. Which is actually just 1, so we're allowed to do this mathematically. Okay, so where does that leave us? Okay, we have the limit now as t goes to infinity. Let's clean this up a little bit. We have 5 plus, one of these t's will cancel out, so we have sine t over t all over, well, t squared over t squared is 1. And we know from part A that the limit as t goes to infinity of sine t over t is 0. So that just leaves us with the limit as t goes to infinity of 5 over 1, which is simply 5. Now here's a graph of that function from part B, and we can see that the limit as x goes to infinity does indeed look like it's going to be about 5. Right, here's 5 right here. So yeah, it looks like it's going to approach 5 if we go out here, like more and more and more. Right, so luckily we don't need the graph though. The graph is just extra because we were able to solve it analytically. Let's take a look at parts C and D. For part C, we have the limit as t goes to infinity. Let's make that x goes to infinity to be consistent, right? Otherwise, it's somewhat meaningless. There we go. X goes to infinity of negative 3x to the 16th plus 2x plus 3. When you have a polynomial and you're letting x go to infinity or to negative infinity, the only thing you need to look at is the leading term, because that's what's going to drag this thing off. You know your answer is either going to be infinity or negative infinity. That's actually a property of polynomials. You prove that eventually in an abstract algebra course or an analysis course. We'll take it on faith for now, and we only need to look at this leading term. So what's it going to be, infinity or negative infinity? And the best approach here, at least the quickest and most direct approach, is just to take this and imagine plugging in some huge number. Let's plug in x equals, 1,000. Right? We're just letting this thing go out to infinity. All we have to figure out is if it's positive or negative infinity. Well, if we had negative 3 times 1,000 to the 16th, I don't know what it is, but I know it's going to be big, and I know it's going to be very negative because it's negative right here. So that tells me that this whole limit is negative infinity. And that's essentially the reasoning you go through for polynomials. It's as rough as that. You just plug in a really big number and see what happens. Let's look at D. It's the same idea for D. We have the limit as x, not t, x goes to negative infinity of the quantity negative 3 x to the 16th plus 2x plus 3. So again, we don't need to look at anything except for the leading term. So we're only looking at negative 3 x to the 16th. We're going off to negative infinity. So just let x be some huge negative number. I don't know, like maybe negative 1,000. Negative 1,000, negative 100, negative 1,000,000. If I plug that in here, so we have negative 3 times negative 1,000 to the 16th. Negative 3 times negative 1,000. I don't want to get too into actually evaluating this because we're not trying to get an actual number. Negative 1,000 to the 16th is going to be positive, right? That's all positive because 16 is an even exponent. So that changes this whole thing to positive. But then we're multiplying by a negative 3, which changes the whole thing to negative again. This is a polynomial, so there's only two possible answers, positive infinity or negative infinity. Indeed, this one is negative infinity. So we'll just write it down here, equals negative infinity. And here's just a quick graph of that function from parts C and D. And you can tell that as x goes out to infinity, the function is clearly going down to negative infinity. And as x goes to negative infinity, the function is still going down to negative infinity. Exactly what we'd expect to see from our analytical results.